In 2019, a company in China put up a 10-story apartment building in 28 hours. Not 28 days, 28 hours. Cameras were rolling the entire time, and the footage looks so fake that most people who see it assume it is sped-up video of a video game. It was not. Every wall of that building was manufactured hundreds of kilometers away, in a factory, on an assembly line, the same way a car door gets stamped out. The floors arrived on flatbed trucks, with the wiring already inside them. The bathrooms arrived fully tiled, with the toilet already bolted to the floor and the mirror already hanging on the wall. Cranes lifted each piece into place. Workers dropped steel pins through pre-drilled holes, and the whole thing locked together like an enormous plastic construction toy. And here is the part that really breaks people's brains. Some of those pieces were not even poured into molds. They were printed, layer by layer, by a machine the size of a warehouse, squeezing out concrete like frosting on a cake. If you are enjoying videos like this one, hit the like button, because these take a long time to put together, and subscribe so you do not miss what comes next. What you are about to hear is the story of how one country decided that building a building the old-fashioned way, brick by brick, in the rain, on a muddy site, was a problem worth deleting entirely. It involves robots, giant nozzles, steel sleeves filled with grout, and a scale of manufacturing that is honestly hard to hold in your head. But to understand why China went down this road, you first have to understand just how badly the old way of building was breaking down. Think about how a normal building gets made anywhere in the world. Somebody clears a piece of land, then they dig a hole, then they pour a foundation. Then, for the next year or two, hundreds of people show up every single morning to that patch of dirt and slowly assemble a structure out of thousands of separate parts, using tools in whatever weather the sky decides to hand them that day. It is a wildly inefficient way to make anything. Imagine if cars were built like that. Imagine if, instead of a factory, Toyota sent 200 workers to your driveway with a pile of sheet metal and told them to build you a Corolla out in the open, over 18 months, in the rain. The car would cost a fortune, it would take forever, and no two cars would come out quite the same. That is exactly how buildings have been made for most of human history, and for a long time, nobody thought there was any other option. For most countries, that inefficiency is annoying but survivable. For China, it became a genuine crisis because of the sheer speed at which the country decided to build. Between 2000 and 2020, China moved hundreds of millions of people from the countryside into cities. That is not a slow drift. That is the largest movement of human beings from farms to apartments in recorded history. Entire cities appeared where there had been nothing but fields. Districts that held 10,000 people were expected to hold 200,000 within a decade, and every single one of those people needed somewhere to sleep, somewhere to work, a school for their kids, a hospital nearby, a road to get there. The construction industry was asked to produce housing at a rate no country had ever attempted, and it did it, mostly with the old method. Millions of workers, on millions of sites, mixing concrete and tying steel by hand. That worked, for a while. But it created 4 problems that kept getting worse, and eventually those 4 problems became impossible to ignore. The first problem was people. Traditional construction is brutally labor-intensive. It requires enormous numbers of workers doing, physically punishing jobs. For decades, China had a nearly endless supply of them, because young people kept leaving rural villages looking for work. But that supply started drying up. The generation of workers who built the first wave of Chinese cities got older. Their children went to university. They did not want to spend their 20s carrying steel bars up scaffolding in 40-degree heat. Construction sites started struggling to fill positions, and wages climbed. The cheap labor that made the old method viable simply stopped being cheap. The second problem was waste. On a traditional site, a shocking amount of material never becomes part of the building. Concrete gets over-poured, and the excess hardens on the ground. Steel gets cut to the wrong length. Timber formwork, the wooden molds used to shape wet concrete, gets used a handful of times and then thrown out. bags of cement get rained on and ruined. Studies of Chinese construction sites found that a meaningful percentage of everything delivered to the site ended up in a skip instead of in the building. Multiply that across millions of projects, and you are throwing away materials on a national scale. The third problem was dust and noise. This one is easy to underestimate until you live next to it. A construction site is a machine for producing airborne particles. Cutting concrete, grinding steel, mixing cement, driving trucks over dirt. Chinese cities were already fighting serious air quality battles, and in some cities, construction dust became one of the biggest single contributors to the particulate matter hanging over neighborhoods. When smog levels got bad enough, local governments started simply banning construction work for weeks at a time. Imagine trying to run a construction company when the government can shut down every site you own with a day of notice because the air is bad. The fourth problem was quality control. And this one is the quietest, but maybe the most serious. When you build outdoors, you cannot control conditions. Concrete that cures in freezing weather does not develop the same strength as concrete that cures at 20 degrees. Rain during a pour changes the water content of the mix. A tired worker at the end of a 12-hour shift ties reinforcement slightly differently than a fresh worker at the start of one. None of these things necessarily cause a building to fall down, but they mean that every building is a little bit of a mystery. You do not really know what you got until it is standing. So you have an industry running out of workers, wasting materials, choking cities with dust, and producing inconsistent results. Being asked to build faster than any industry in history has ever been asked to build. Somebody was going to suggest doing it differently, and the suggestion, when it finally came, was almost insultingly simple. Stop building outside. Build inside. Take the entire construction process, pick it up off the muddy site, and move it into a factory where the temperature is controlled, the machines are precise, the materials are measured to the gram, and nobody has to work in the rain. Then take the finished pieces, put them on a truck, and assemble them on site. That idea is called prefabrication, and it is not new. Versions of it have existed for over a century. The Soviet Union built entire cities out of precast concrete panels. Britain threw up prefab housing after the Second World War. Japan has been quietly making excellent factory-built homes for decades, but China did something different with it. China did not treat prefabrication as an experiment or a niche. China decided to make it national policy and then push it at industrial scale, and in the process, it started stapling on technologies that the older prefab systems never had: robotics, digital modeling, and, in a growing number of projects, actual three-dimensional printing. Let me walk you through what one of these factories actually looks like, because it is not what most people picture when they hear the word construction. There is no dirt, there is no scaffolding, there is a long, clean, brightly lit building that looks far more like an automotive plant than a building site. Down the middle runs a production line, and moving along that line are steel molds, each one shaped like a section of wall, a slab of floor, a flight of stairs. The line starts with the mold being cleaned and oiled by a robotic arm so the finished concrete releases easily. Then a plotter, a machine on rails that works like a giant inkjet printer, draws the exact outline of that specific wall onto the mold surface. Not a generic wall. That wall, for that apartment, on that floor, of that specific tower. The design comes straight out of a digital model of the whole building, so every dimension has already been checked against everything it will eventually touch. Workers or robots then place the steel reinforcement cage into the mold, following the lines the plotter drew. Then, the interesting part, before any concrete goes in, they install everything that will need to be inside that wall for the rest of its life. Electrical conduit, junction boxes, sockets, insulation, sleeves for plumbing, the window frame itself, positioned to the millimeter. In a traditional build, all of that gets chased into the wall afterwards by somebody with a grinder, cutting channels into concrete that was perfectly good until they cut it. Here, it is simply built in from the start. Then the concrete arrives, not in a churning truck that has been driving across town for 40 minutes, slowly changing consistency the whole way. It comes from a batching plant 50 meters away, mixed to a recipe measured by computer, delivered by an overhead hopper that travels along the ceiling and pours exactly the volume required. Vibration tables underneath shake the mold so the concrete settles into every corner and the air bubbles rise out. Then the mold goes into a curing chamber, which is essentially a giant heated locker, where warmth and humidity are held at the perfect level for the concrete to gain strength as fast as physically possible. What takes weeks on a job site takes hours in there. The panel comes out, gets lifted upright by a machine called a tilting table, gets its surface finished, gets a barcode or a chip attached that identifies exactly which building and which position it belongs to, and goes into the yard to wait for its truck. The whole time, that panel has never been rained on, never been dropped, never been guessed at. But this is where the story gets genuinely strange. Because for some of these components, China stopped using molds altogether. Concrete three-dimensional printing works on the same basic principle as the desktop printers people use to make plastic figurines, just scaled up to an absurd degree. A nozzle moves along a programmed path, extruding a thick paste, laying it down in a continuous ribbon. Then it rises a couple of centimeters and lays down another ribbon on top of the first, then another. Layer by layer, a wall grows out of nothing. The material is not ordinary concrete. Ordinary concrete is far too runny. If you squeeze normal concrete out of a nozzle, it would slump into a puddle. The mixes used for printing are specially engineered to do two contradictory things at once. They have to flow smoothly through a hose and out of a nozzle without clogging, and then, within seconds of landing, they have to stiffen up enough to support the weight of the next layer without squashing. Getting that balance right involves fine sands, chemical additives that control setting time, and often fibers mixed through the material to hold it together. Chinese firms have printed some genuinely eye-catching things with this. A company in Shanghai printed a row of small houses and assembled them in a single day, which got worldwide attention around 2014 and put the technology on the map. A construction group printed a pedestrian bridge in a Shanghai park, a graceful arched thing inspired by an ancient stone bridge design, made in modules and clicked together on site. Researchers printed a section of the Great Wall as a demonstration. A two-story villa was printed in place, on site, with a gantry printer built over the plot. And here is the crucial thing that most coverage of this technology gets wrong. The exciting part of printing is not that it replaces the factory. The exciting part is that it lets you make shapes that a mold cannot make cheaply. A steel mold is brilliant if you want 1,000 identical walls. It is terrible if you want 1,000 different ones, because every unique shape needs its own mold. And molds are expensive. A printer does not care. Printing a curved wall costs the printer exactly the same effort as printing a straight one. You just change the file. That means you can hollow out the inside of a wall in a lattice pattern to save material and weight. You can build in curved channels for pipes. You can make every panel on a facade slightly different so the building does not look like a filing cabinet. So what is emerging is not a world where printers replace everything. It is a hybrid. Standard, repeated components, floor slabs, straight walls, staircases, get made in molds on the production line, because that is fastest. Complex, curved, one-of-a-kind, or hollow components get printed, and both come out of the same factory, get loaded onto the same trucks, and go to the same site. But making the pieces is only half the problem. Now you have to connect them. This is the part that separates a serious engineering system from a gimmick, and it is where the Lego comparison starts to strain, because Lego bricks just clip together and a Lego tower falls over if you sneeze on it. A 20-story residential tower in a seismic zone cannot do that. The dominant solution in China is a system built around something called a grout sleeve. Picture a steel tube, closed at the bottom, sitting inside a concrete column, cast in place when that column was manufactured, with its open end flush against the top surface. Now picture the column below it, which was manufactured with steel reinforcement bars sticking straight up out of its top face like whiskers. The crane lowers the upper column so those protruding bars slide down into the waiting sleeves. Then workers pump a specialized high-strength grout into the sleeve through a small port on the side. The grout fills every gap around the bar. When it hardens, that connection is not just holding things in position. The steel bar and the sleeve are locked together so completely that the join is stronger than the bar itself. If you tested it to destruction, the bar would snap somewhere along its length before the connection let go. Do that at every column joint, all the way up a building, and the vertical steel skeleton is effectively continuous, exactly as if the whole thing had been poured as one piece. Floors work slightly differently. Very often the floor slabs that arrive from the factory are only the bottom half of the finished floor. They have reinforcements sticking up out of their top surface and a deliberately rough finish. Once they are sitting on the walls, workers lay additional steel across the top, tying the slabs to each other and to the walls, and then pour a layer of ordinary concrete over the whole floor. That wet layer bonds to the rough precast surface and turns dozens of separate panels into one continuous concrete plate. That plate matters enormously. In an earthquake, the floors are what stop a building from twisting itself apart. They tie every wall together and force the whole structure to move as a single object. So, the honest description is not that these buildings are clicked together like toys. It is that they are precision manufactured in pieces, assembled dry, and then stitched back into a single monolithic structure with steel and grout at the joints. The speed comes from the fact that almost all the slow work already happened indoors, which raises the obvious question, and it is the question everybody asks: is a building like this actually safe? The engineers involved have been asked this so many times that testing has become an industry of its own. In laboratories across China, full-scale sections of precast buildings have been bolted onto shake tables, enormous hydraulic platforms that can reproduce the ground motion of recorded earthquakes and shaken until something fails. Individual connections have been clamped into testing rigs and pushed back and forth through thousands of cycles to simulate decades of loading. Joints have been deliberately built badly, with grout voids and misaligned bars, to find out how much error the system can tolerate before it becomes dangerous. The consistent finding from that work is that a properly executed precast connection performs at least as well as a traditional poured joint, and sometimes better, because the concrete around it is stronger and more uniform. The failure modes, when they happen, are almost always about workmanship. Grout that was not pumped all the way to the top of a sleeve, a bar that was bent to fit, a joint that was not cleaned before assembly. And that is a real vulnerability. And I do not want to sell you a fairy tale here. The entire system depends on the assembly crew doing a small number of things absolutely correctly, and those things are hidden inside the structure the moment they are finished. Nobody can see whether a grout sleeve is fully filled by looking at the wall. Chinese regulators responded with inspection regimes, camera systems, sensors that confirm grout has reached the outlet port, and traceability requirements that let an inspector scan a component and pull up its entire manufacturing record. Whether that gets followed on every project, in every province, by every contractor, is a fair thing to be skeptical about. Building codes are only as good as their enforcement, and China's construction sector is enormous and not uniformly disciplined. That skepticism is healthy, but it should not obscure how effective the system is when it is done right, and the clearest demonstration of that came in the most dramatic way imaginable. In early 2020, in the city of Wuhan, authorities needed hospital capacity that did not exist. Existing hospitals were overwhelmed. The decision was made to build a dedicated facility from scratch, and the timeline given was 10 days. That number sounds like propaganda until you understand what actually happened. The building was not conventionally constructed at all. It was assembled from prefabricated modules, boxes manufactured elsewhere and trucked in, each one containing a finished room with walls, ceiling, ventilation, and services already installed. Ground crews prepared a flat, drained, serviced platform. Cranes stacked the boxes, Teams connected power, water, air handling, and medical gas between units. Round-the-clock shifts, thousands of workers, hundreds of machines, millions of people watched it happen on live streams. And the reason it could happen at all is that China had already spent a decade building the industrial capacity to produce those modules. The hospital was not a miracle of improvisation. It was a stress test of a supply chain that already existed. Sitting behind all of this, and rarely mentioned, is the software. None of it works without an extremely detailed digital model of the finished building, built before anything physical is made. Not a drawing. A model in which every wall, pipe, duct, cable, bolt, and window exists as an object with properties. The reason that model is not optional is simple. On a traditional site, mistakes get fixed on the fly. A pipe collides with a beam, somebody notices, somebody grinds a notch, life goes on. In a factory system, a collision like that is a disaster. The wall is already cast. The pipe is already inside it. You cannot negotiate with hardened concrete. So every conflict has to be found and resolved in the model first, months before manufacturing begins. That model then feeds everything downstream. It tells the plotter where to draw. It tells the robot where to place reinforcement. It generates the barcode on each panel. It tells the logistics team the order to load trucks, because the crane has to receive components in exactly the sequence it will install them. On a site with no storage space, a truck arriving in the wrong order stops the entire operation. So the real product is not the panel. The real product is a synchronized system, and the panels are just what it happens to be made of. Now let us talk about whether any of this is actually worth it, because there is a persistent and legitimate argument that it is not. The case in favor is straightforward. Assembly on site can cut construction time substantially compared with conventional methods, sometimes by a third or more. It needs far fewer workers on site, which matters in a country with a shrinking construction workforce. Waste drops dramatically because a factory can reuse formwork thousands of times and recycle offcuts internally rather than skipping them. Dust and noise in residential neighborhoods fall off a cliff since the loud, dirty processes have moved to an industrial zone. And safety improves because most of the work happens on a factory floor rather than at height on scaffolding. And falls from height are the single largest killer in construction worldwide. The case against is equally real. A precast factory is an expensive thing to build, and it only makes financial sense if it runs near capacity. That means it needs a reliable pipeline of nearby projects, because concrete is heavy and shipping it far destroys the economics. A panel that travels 300 kilometers has burned through its cost advantage in diesel. So the system works beautifully in dense regions with constant demand and badly in remote ones. It also punishes uncertainty. Traditional construction is flexible. A client can change their mind in month 8 and you can adapt. In a prefabricated project, the design has to be frozen very early because manufacturing starts before the site is even finished. Late changes are ruinously expensive. That trade, flexibility for speed, does not suit every client or every kind of building. And then there is the aesthetic complaint, which people raise constantly. Does this produce endless, identical gray boxes? Historically, yes. The Soviet panel blocks are the reference point everybody reaches for. And they were monotonous. But that monotony was a product of the technology of the time, when tooling was crude and every variation cost real money. Digital fabrication has weakened that constraint considerably. When the shape of a panel is defined by a file rather than a fixed mold, variety stops being expensive. Facades can be textured, angled, colored, and varied across a building at close to no additional cost. Whether developers choose to spend that freedom on good design is a separate question, and often the answer is no. But that is a decision, not a limitation of the method. Beijing and Shanghai now mandate that a significant share of new construction must use prefabricated methods, with targets written into policy and rising over time. provinces publish their own percentages, developers get preferential treatment for hitting them. That is not a market that drifted this way. It is a market that was pushed. And the push is producing something that goes beyond faster buildings. It is turning construction into manufacturing, and manufacturing behaves differently from construction in one crucial respect. Manufacturing improves. A construction site is a one-off. Whatever the team learns, they learn on that project, and then they scatter. A factory is permanent. If a panel type keeps cracking during transport, the factory notices, changes the lifting point, and never has that problem again. If a connection detail is slow to install, someone redesigns it, and every future building benefits. Errors get engineered out permanently instead of being rediscovered on every job. That compounding effect is why cars got better every decade, while houses mostly did not. Layer three-dimensional printing on top of that, and the trajectory gets more interesting still. Printed components can be hollow in ways molded ones cannot, which means less concrete per wall, which matters enormously given that cement production is one of the largest single sources of industrial carbon emissions on the planet. If you can build a wall that performs identically using significantly less material, that is not a design flourish. That is a meaningful climate lever applied to one of the dirtiest industries there is. Research groups in China are already pushing further. Printers mounted on mobile robots that drive around a site rather than sitting inside a fixed gantry. Multiple printers working on the same structure simultaneously, coordinating their paths. Mixes that incorporate crushed recycled concrete from demolished buildings. So the material for tomorrow's printed wall comes from yesterday's tower. Put all of that together and you can see the shape of the thing being built. Not just apartment blocks, an industrial pipeline where a building is designed as data, manufactured as components, tracked individually, shipped in sequence, assembled in days, and eventually taken apart and fed back into the same system. That last part is worth sitting with for a moment. A building assembled with bolted and grouted connections is, in principle, a building that can be unbolted. Some engineers are already designing with that in mind, treating a structure as a temporary arrangement of components rather than a permanent object. A tower that comes down in 30 years might not become rubble. Its slabs might become the floors of something else. Whether any of that arrives at scale is genuinely uncertain. Plenty of promising construction technologies have stalled. The economics only work under specific conditions. The quality control depends on human beings doing unglamorous work correctly on a Tuesday afternoon with nobody watching. And there is a fair argument that China has built too fast, too much, and will spend the next decade dealing with the consequences of building at all, rather than how it built. But the machines exist. The factories are running. The buildings are standing, and people are living in them right now, in apartments whose walls arrived on a truck, with the light switches already installed. The thing that is actually being replaced here is not the bricklayer. It is an assumption. The assumption that a building is something you make in the place where it will stand. Break that assumption, and construction stops being a craft performed outdoors and becomes a product manufactured indoors and delivered. If you enjoyed this breakdown, leave a like and subscribe. Every week we dig into the technologies, factories, and enormous engineering systems that are quietly reshaping how the world gets built, the ones almost nobody talks about. Turn on notifications so you catch the next one. There are related videos on screen right now if you want to keep going. So here is my question for you. If your home could be manufactured in a factory and assembled in a week, would you actually want to live in it? Or does something about that idea bother you? Tell me in the comments. Is less than